Great. And, you know, I've met one person in Singapore so far who pronounced my name correctly. It's very good. Schlossnagle is a tough one. I'm Theo Schlossnagle. That's incorrect. I'm not actually the CEO anymore. I'm the CTO of Circonus. We do large-scale telemetry analysis. We build like a distributed time series database and take machine data and try to figure that out. So what's kind of interesting about what we do is that we built the service as a SaaS because everybody gets to send their data into the cloud and use the cloud these days. And what we found was that a lot of the types of customers we sell to require on-premise installations. So as is typical in a SaaS, you have lots of moving parts and you have really prescribed operational kind of doctrine that's there. And trying to take all of your software, all of that complexity, all of the release schedules, and then all of like the kernel knowledge from your organization to run that software and ship it to somebody is actually really hard. So I will say, this is kind of a general statement of everything. Software is horrible. Computers are pretty horrible. I think the more that you work with them, the more you realize that they shouldn't actually work, and the internet shouldn't work at all. I mean, it's amazing DNS even works most of the time. If you ever have like shoddy Wi-Fi in a hotel and the internet all falls apart, to me, it's sort of amazing that the whole internet doesn't always fall apart all the time. But once you've built really large stacks, so in our system we have, it's not super large, but the core of our system has about 18 different components. They're kind of like macroservices. They all talk together along various protocols, mostly REST-based, a little bit of tighter RPC. But one of the things that we do oftentimes to make up for the fact that all of the software that we build on has bugs, I mean, everywhere from the firmware to the libraries they use to the software that we write in-house, we end up putting a lot of operational knowledge and making things work. So what I want to do, I already answered why we ship software, it's because clients want it shipped. I wanted to go over some rules that sound pretty obvious to SREs in general, like some kind of paradigms for building software, and then talk about kind of how we can deliver that into the software instead of into the organization. So the beauty of doing that is that, does anybody here work on open source software? Anybody? Yeah. Does anybody have their software run by someone who's outside their organization? So if it's open source, by nature, it should be used outside of the organization, right? So if you like work on a library, everything from like a Node.js package to a C library somewhere, if it's adopted by another organization and used, there's someone operating your software that isn't you, it's not even in your organization. So all of your organizational knowledge on how to make that work and how to like not bleed to death when you get stabbed by that product is really hard to give to that other person. So you kind of need to codify it and put it in the software itself. So what are the rules? General rules of running any sort of large-scale service is that crash landings should be fast and controlled, so things should not be broken or disabled in production for a really long time. They should just explode. And then you should have all of the pieces to analyze them, and you should be able to bring it back online, which takes us to postmortems. So postmortems are fundamental. The old IT joke of have you tried turning it off and turning it on again is largely embarrassing to the world of software engineering. Okay, if you don't understand why your software failed, you have absolutely no right to say it'll never fail again, right? So when something goes wrong in your software, it's kind of a fundamental responsibility of software engineers to dive in, understand the pathology of that failure, and be able to navigate to a remediation for that, like to be able to actually solve the problem. Circuit breakers are pretty obvious. You basically want things to fail quickly. And I think that there's like a general premise that the behavior of our software is really complex, especially when you leave the world of monoliths. So when you're in complex systems with any sort of distributed systems or microservice-based approach, if you're running on Kubernetes or something like that, even more so, the behavior of the system is really complex, and you owe it to yourself to understand the complexity that's there. That should be a slight motivating factor to keep things as simple as possible as well. Another is having a failure budget. And then at the end of the day, what it really means is that all of this stuff is going to break. You're going to be served up problems you've never seen before. And being able to understand the system requires instrumenting that system and being able to observe how it behaves. So I'm going to go through each of these and talk about what we do. And it's important that we're able to kind of ship this out to customers as well. So crash analysis, right? So if you don't understand why it failed, you do not know anything about the failure, right? So if you have a product that's seg faulted or throw a stack trace or malfunctioned, you have to be able to interrogate that software. And a lot of times that software is not running anymore. It actually crashed. So I also encourage people to interrupt me and ask questions. I'll be happy to repeat them into the mic. So how many people here write programs in C or C++ or Go or Rust? All right, so those are the good languages. How many people write in other languages? Yeah. So all languages are good languages. All languages are bad languages. But so if you're writing in a low-level systems language, usually the only evidence that you've had a serious malfunction is that you get a core dump. And if anyone has ever tried to analyze core dump, they're not too complicated. On Linux, it's just an absolute travesty that after all of these years, they still don't include the ELF binary for the thing inside the core. So you can give someone a core, and they're like, what am I supposed to do with this? Right? You have to give them the binary that produced it as well, which is remarkably stupid because the core format can actually include the binary in it. I don't know why that doesn't happen. So if you've ever tried to get a customer to give you a core file, that is much harder than actually analyzing the core file, where it's like, I need all the bytes. Just send me. And they're like, oh, it's like 6 gigs. How do I give it to you? It's a conversation you don't want to have. So one of the things that we use this product called Backtrace. And what it does is it basically takes a mini dump style, sort of like a Windows mini dump of a core, and it ships it up to us automatically. So when our software fails in the field at a customer site, it drops this little like couple 100 kilobyte file, which is a trace file. And then if they open their network up, it'll send it up to a catalog server of ours. And we get to see the trace. So an engineer gets immediately notified in Slack, you have a crash, this is the backtrace. They click on it, they can see all the stack frames and stuff like that, and they have sort of an answer to that problem. A lot of times we solve those problems before the customer actually knows about it. And the reason is when your software crashes, it should restart itself, right? Like you should always have a resilient sort of self-healing sort of framework in your system. So one of the things that we find, this is kind of a workflow for something. One of our components in the system is called a broker. It's written in C and in Lua. There's a little bit of Java in there too. If it crashes, within 1 second, we get a Slack notification. An engineer probably responds to that in 1 to 2 minutes if it's during working hours. They go in, simple, like say a null pointer dereference or some sort of linked list manipulation problem, and they're like, oh, no, that's stupid. They go fix it, they commit the change, they get a review, goes into GitHub, goes through the CI environment, build and test, goes into packaging, goes into the packaging repository, and then it gets deployed. So we have many, many cases where simple bugs, when it crashes, there's a 23-minute turnaround through the entire CI/CD process to deploy that to every field, every broker in the field. We have hundreds of those that are around the globe. That's really good for like a C app. Right? It's not easy to get production code out on client machines inside of half an hour. Usually it's like 2 weeks in most organizations. And a lot of that has to do with kind of seamless stack trace and failure reporting and having a really tight, complete CI and build and deployment cycle. So that's really, really useful. There's a whole bunch of services out there that do this. Backtrace is one. There's like Sentry. I think I can't remember the other names of those, but basically crash analysis things and your JavaScript apps, like even web apps, can report stack frames from bad JavaScript into these apps as well. So you can get a robust full catalog of all the failures you're experiencing in production. And those are really fantastic. So near and dear to my heart, the other thing is that you should always expose telemetry. So I usually tell this through an anecdote, and it usually has an anecdote of putting a software engineer into an operational role and having them look super stupid, and it's great. And if you've been a software engineer and you've never been in operations, you think your software's great, you realize you have bugs, but you know your software. And then you deploy the software, and there's some sort of performance regression, and you're sitting there with an ops engineer, and you're like, this makes no sense. Like every problem statement starts with, this doesn't make any sense. This is not going to work. The only way this could be possible is if this linked list had like over 1,000 items in it. To which the ops engineer says, well, does it? And they go, I don't know, I need to get you a new binary, right? Like I need to put a printf in there or something like that, right? So once you've written software and deployed it to production and had it misbehave, the idea that you can redeploy that software with changes to kind of better observe it is unacceptable, right? Once you're in operations, you want to be able to observe that software. You want to instrument it. You want to be able to interrogate that software and ask what it's doing at any point in time. So there are some really magical tools that have been around for a while. One of them is dtrace. But eBPF in Linux allows you to kind of ask questions that you didn't anticipate. But generally speaking, when you're writing software, you really want to overexpose. Basically, everything in the system should have telemetry. You don't have to collect it or graph it or store it, but it should be there. So when your software starts to behave in weird ways and you have these odd questions about how big is this data structure, what's the runtime of this function, that you have that information available to you. So one of the things that we spent a lot of time building is a C library called libcircmetrics. It's BSD licensed. It's very, very fast. Focuses on multi-thread, lockless approaches to that stuff. And it supports some pretty basic things, right? So like text metrics, you can log the versions of software and statuses and things like that. It supports the classic numeric things like gauges and counters. And it does all the clever stuff like automatic CPU fan out and lockless shifting of counters. And then one of the really neat things that it does that most others don't is it has first-class support for histograms. So we use these log linear quantized histograms, and they have a flat 9 nanosecond recording time. So you can actually use them in really hot software. So if you want to track the latency of function calls or track the number of disk blocks you're writing or the size of disk blocks, size of write payloads, network packet sizes, anything like that. As long as what you are measuring is relatively large compared to 9 nanoseconds, it's a pretty good fit with low overhead. And then all of the metrics in there, you have to name them, of course, to be able to ask questions about them. It supports kind of like the old dot delimited graphite style format where you had this huge metric name, and it simultaneously supports a much nicer kind of multi-dimensional tag annotation system as well, and you get JSON output. So it's pretty great. So some kind of code samples. I haven't had code samples in slides in years. But this is this C code, but it's basically setting up a whole bunch of different things that we're going to track. This is a snippet from some database code where we're tracking the number of writes and reads and things like that to the system. So these are setting them up, telling it what type they are, setting the units on them and things like that. And then this is basically the code that would instrument it. So the thing we are doing is the line marked with O, which is some sort of database put. And then all of the rest of it is instrumentation around it that does timing. So we get what time it is, we do the call, we get what time it is again. Then we track the latency in a histogram. We track the number of tuples that we modified in a histogram. So we know, like, of all of the calls, exactly how many things were modified. And then we count some things. So it's pretty straightforward. But the beauty of that, people think, okay, great, so I'm counting things, I have some metrics. Being able to get those metrics out at runtime and visualize them so that you can see in your database that your latency profile is a trimodal histogram like that is amazingly useful. So you go into the system and you're like, I think my database is slower. And you pop up a histogram that shows exactly the latency in nanoseconds of every single call that's been made to that endpoint. Or in this case, written. In this case, it's actually read out of the database. So this is really good. So the histogram support in there is libcirclehist, and it has a fixed about 4.3% error a maximal. So it's actually a really accurate tool for that as well. So there's a font problem. So we've talked about crash analysis post-mortem. We've talked about instrumentation and putting metrics in your software to ask questions. Those things are really useful for understanding like performance regressions of individual components or function or safety regressions of individual components. But as we all know, as systems get big and distributed, understanding distributed state and how those systems work becomes incredibly important. And I would say that this is one of those problems where the industry's pointed in the right direction, but I will say that the offerings out there to kind of just solve this for you are wholly underwhelming for the types of things that we've wanted to do with it. So if nobody's seen a distributed trace before, it actually looks a lot like a HAR from a browser. So instead of looking at all the elements on a page that get loaded, you're actually looking at interactions between service components in the system. So this is like a sample request of somebody loading a graph out of our platform. Somebody comes in, loads a graph. It's a JSON request, and then it goes back and does a map and reduce over a distributed database. So this thing has 92 little jobs 96 little jobs that it does, and I can see where they're laid out. And the nice part about this is if any of them look really interesting, I can expand that and get some more details about that. So the reason I say that they're a little bit underwhelming, this is super useful in general to try to understand exactly where you have a failure or where you have a performance regression in a large, complicated system where if you go in and you're going to make 1,000 different RPC calls and call 38 and call 92 are slow, that's really hard to just guess, right? It's actually hard to read log files to do that. You really need good tooling, instrumentation to be able to tell you that and let you explore that. So the problem in general is that we only retain our traces for a very short period of time. And the reason is that if we turn the debugging on in the tracing, a single trace can produce 4 gigabytes of data. So a normal trace runs, say, like a request that takes 150 milliseconds. It can produce about 400,000 spans, 400,000 of those things, and 4 gigabytes of data. So I don't want to send that out of my network because it's just too expensive. And it's incredibly useful for debugging, but I can't turn it on most of the time. So in our system, even in low volume with like moderate sampling, we end up hitting around 30,000 traces a second, which if you look at kind of the spread in the industry, and that's with sampling, it's ridiculously expensive to use a third-party service to put the data in, which is unfortunate. So we kind of, in our environment, we just stick that in a Cassandra node and reboot it every 3 days. Just like wipe it out and restart it. And that's all for cost controls, right? I just put the data in there, and it's there for engineers to analyze problems that are happening right now. So you get a customer service complaint that says, hey, I load this graph and I get the wrong data, or I load this graph and it took too long, or whatever. I did X, Y, Z, and I thought ABC was supposed to happen. They can go in and find that request and map it through the entire service framework and try to figure out all the details. And then occasionally when the problem is hard to debug, they'll reproduce the problem and then add our kind of secret headers in there that cause that huge 4 gigabyte trace dump to come in. And then they can really explore everything. So we use an application framework called libmtev, which is BSD licensed, open source C library for building systems. And it has all of this tracing support in it. What's kind of cool about that is when that header's turned on, every debug message in the system kind of lights up, turns on, and attaches the debug messages to the trace instead of to the log file. So you get like everything. It's like Pandora's box opens, and then you have at least a day's worth of work to like find what happened. So it's pretty interesting. But it's kind of weird as an observability tool. We use it for observing current state, but we do not use these traces to really analyze long-term behavior. And the reason for that is just that the pricing dynamics are really, really horrible for that. So the tech involved in that, so this graph comes from a product called Jaeger, which is an open source project out of Uber. And so Jaeger can take in open tracing data and Zipkin data. And we submit Zipkin data for that. So if you're looking to implement that, it's usually pretty quick. If you're writing in Go, I saw a lot of hands go up in Go. The Jaeger stuff is all Go-based. And the instrumentation that they have for Go applications is really tight. It's actually really, really easy to implement. It's probably a couple hours to implement it in whatever framework you're working in, and suddenly you get tracing data throughout your entire system. And the beauty of that is we do something a little bit weird. We publish all of the tracing data to a message queue, and we make it work really, really well when the message queue is not there. So there's like a limited backlog. So normally when we deploy the system, the message queue is not on. So the tracing data kind of gets produced in memory and then thrown away. And then when you turn the message queue on, suddenly the floodgates open and then it all funnels into Jaeger. And the upside of that is that engineers can boot their own sort of Jaeger instances, and they have their own subscribers to that trace data, so you can have multiple subscribers to all of these span. So it's a pretty simple framework. Very powerful, though. The last one, and I have a controversial opinion here, is that logging is trash and you shouldn't write logs. So the main reason is that logs in general are for human beings. They are not for computers. Because if you ask a computer to talk to another computer, I guarantee you they have something better than logs to do that. So really producing logs to be from a computer to be consumed by a computer just meant you use the wrong format. You should probably not even be using JSON. You should probably be using something like protobuf or Avro or Thrift or Flatbuffer or something like that. Because you're going to be paying to serialize it out and paying to read it in. It doesn't make any sense. So if you're writing logs, they should be for humans. And if you have large enough systems that you're trying to manage, you really shouldn't have humans involved in that process in the first place. So really logs are for engineers or software engineers to kind of dissect and debug systems, classic printf style stuff, but I'm not a fan of logging in general, because every time I find a log that I wanted, it should have been read by a computer somewhere else into a tool. So down with logging. And your Splunk bills go to 0, which is great. So one of the things that I see that happens a lot, and I think specifically in our industry recently, is this idea of kind of event-driven debuggability and observability by solving the unknown unknowns. And I feel like at some point marketing got hold of the word unknown unknown and then just used it how it wanted to. So when you think about known knowns, unknown knowns, known unknowns, and unknown unknowns, if you go into your system and you can ask it a question and get the answer, and you've instrumented your system for that. So for example, in tracing platforms out there, there's a lot of tracing platforms where you can emit events. It's not an unknown unknown if you went and emitted an event. You knew to emit event there, right? So you fundamentally know one of the things, like, I'm probably going to have a problem here. So you emit some sort of event, and then later you're able to analyze that and perhaps answer questions you didn't anticipate. So you didn't know quite what the question was, but you knew that it was important. So in distributed systems, in complex systems, there are a lot of unknown unknowns, which means you don't know what the problem is, and you certainly didn't know that you needed to get that data to answer the question, right? So you don't know the question, and you don't really know ahead of time what data you need to answer the question. And amazingly, we have good tools for that too. So if you haven't looked at eBPF and BPF trace from Linux, they're relatively new in the Linux user space. But they're really, really powerful. dtrace has been around for quite a long time, but they provide a lot of the same facilities as that. And they're pretty powerful systems, but imagine that you're on a Linux box and you have root, so you can do anything you want. I mean, literally anything you want. You can go in and change any memory on any process. What it allows you to do is go and dynamically instrument basically anything in the system. You can dynamically instrument any function boundaries in the kernel. You can dynamically instrument the job scheduler in the kernel, memory allocators, disk subsystem, and in some versions of this, you can instrument dynamically any machine code in any process anywhere. Which means that if you didn't put a printf statement somewhere to figure out something, you can do it now while it's running in production already. So this is really kind of the unknown solver. So personally, when I hear a lot of ops people say no one should ever be able to SSH to a server, right? Like you shouldn't be able to do that. All of its all the operations should be codified. Like that kind of flies in the face of if something's broken, it's your job to understand why. Right? So if there is a process that's broken and malfunctioning, and turning it off and on again is a really shitty answer to that. You should not do that. You should, assuming you have the resources to do it, have someone do a full triage and diagnosis. So the poor man's way of doing that is that you go in and you crash the process and retrieve a core file, and then you go analyze it later. But if anybody's ever done anything with a core file, it's usually pretty hit or miss. Some of the more complicated problems, you need 100 cores around a specific problem to really kind of get all of the angles at the problem before you figure out what it is. But if that process is still running and still malfunctioning, and you can start asking it leading questions with something like dtrace or eBPF, you can really take that to the next level. You can go in and basically rewrite your app while it's running in production to get diagnostic information out of it. It's magical. Really, really cool. And we use this all the time because we write a lot of high-performance software, and a client will come in and say, this is slow, and we're like, I wish I knew how long that specific reduction function was taking in their case. 5 lines of scripting and a BPF trace later, and I actually have nanosecond level instrumentation around that function, and I get the answer in their environment on the system with the problem. So I don't have to go through the work of repeating the problem, and I don't have to go through the work of producing new binaries to instrument and all that stuff. The other really cool thing you can do with eBPF and dtrace is that you can instrument things that are pretty normal. So one of the classic problems in computing is that we don't all have the benefit of working on stateless systems. We write database software, but I'm sure you store stuff somewhere too. It's kind of important to know how long it takes to store things. So disk performance is still an issue in the world. That's why they keep making faster disks. So for a very long time, I would say the last 20 or so years, the classic way to observe disk performance is to track like the average latency of transactions on a disk. So if you run like IOStat or SAR, you'll get average transactions against SDA on Linux is 11 milliseconds or 2 milliseconds or 100 micros, depending on what type of hardware you have. With eBPF, you can actually instrument every single I/O operation. So instead of saying what's the average sort of made sense back in the day when we did like 150 a second. Even that didn't quite make sense. But on an NVMe card, it's reasonable to do 500,000 I/O operations per second on a box. So telling me the average is like not very enlightening. So what's really interesting there is by being able to track every single one of them and put them in histograms, you can actually get these really robust long-term behavioral models of hardware. So this is a graph of a heat map. It's a little hard to see on the screen due to the contrast, but you can sort of see, I don't think my mouse works there, but you can see kind of a band about 1/5 of the way up, and then you can see a band right off of the x-axis. And where that's darker in color, there are more transactions that took that long. So the y-axis in this case goes from 0 to 5 milliseconds. So I have a whole bunch of stuff that's down in the like maybe 0.4 millisecond range, and then I have a whole bunch of stuff that's around 1 millisecond. And I can zoom in on this. So this graph, I don't know, it probably took like a second to load in the system. That's a year's worth of data, and that super thin vertical line is looking at one 12-hour segment where 65 million IOPS happened. So that little pop-up is a histogram of 65 million IOPS. I can see the two modes. There's one mode on the left, there's a bigger mode on the right. Those are the things coming out of an SSD's cache versus an actual SSD. So I can zoom into those minute by minute as well. So this allows you to kind of go back and look at your system in detail on how it behaves. And I think one of the most important things about storing this data granularly over a long period of time, so being able to look at your graphs second by second or minute by minute today and last year, is because every time you do a postmortem, every time something fails, in theory, you learn something, right? Your organization has processes, you do some sort of caucus with people, you do a postmortem, and you come up with new processes, new theories about how things should operate, how things should be run, how things should be analyzed, how incident response should work, right? All of that stuff you learn. Are you right? That's a great question. I've learned this. Am I right with my thesis? I have just had an incident. I think I've learned something. The best way to test if you've learned something is not waiting for the next incident to try it out. That's a pretty junky way. It's probably the best thing that most people do. But the best thing to do is to say, I've learned this thing. Would it have helped me in the incident 3 months ago, and 9 months ago, and 14 months ago? And if you have the granular data around all of the system's performance, you can redo that postmortem without losing any sort of integrity. So being able to redo postmortems with new learned knowledge is a way to prove that knowledge right. I don't think enough organizations do this. A lot of people throw their data away. A lot of people average it over time. So if I go back a year, I've got like 5-minute or 2-hour averages of my data. So I can no longer really do that high integrity postmortem again. So, and then when you hire new employees as well, it's hard to learn on the job with postmortems. It's much easier to run, instead of game days, to run redos, right? You redo the earlier postmortem with all of your new techniques, and you include new staff that haven't done that before. And then when they see an incident, they actually have real operational practice with your organization's data and all of the tools. So that ends up being really important. So this is the part where it gets really controversial. So all of this stuff, probably people have stuff like this. You know when your stuff breaks, you're probably monitoring it, you probably have some metrics around it. Hopefully you have some tracing. That's probably the newest thing that I would guess most people don't have is tracing. The really interesting part that I think we've learned is that having a minimum viable product of each of those things inside the software that you ship is invaluable. And that's interesting. So that's I think the most like the biggest takeaway from our experience in shipping the software. So a lot of people use, Jaeger is a great example of that. So Jaeger is this framework for collecting and exposing trace data. But when I ship my software stack to someone, they're not going to be running Jaeger. I guarantee you, they're just not running Jaeger, so I have nowhere to point that to. The system emits all of these metrics, and you can collect them and graph them and say, like, stack driver. Great, my customer I shipped it to doesn't have stack driver, so now I can't see any of the data, right? Like, you have this problem that if you rely on all of these other services to be able to observe your software and analyze it, it's highly likely it gets deployed in some environment, especially if it's open source. It gets deployed in some environment where accessibility to that, either financial accessibility or just network accessibility to those services doesn't exist. And then all of that awesomeness is completely neutered. Like it's just inaccessible to the user. You have all of this observability, you have all of this instrumentation, and you're telling somebody to like curl it with JSON, you know, curl it and pipe it to JQ. Like it's a horrible, horrible experience. So you kind of want to build a minimum viable product of this stuff to observe your product. So when you deploy, say, a database, I'll use a great example of one that doesn't do this. Redis. How many people here use Redis? Yeah, well, enough people, or Memcache or anything like that, right? So you ship it, and it's got some stats that are kind of built into it, but it doesn't show me a history of its performance. It doesn't track its own latency. It doesn't participate in tracing or anything like that, right? And it could do it for cheap. Like it's really not that much work. And and ideally, I don't actually have to use that because I plug it into my stack driver or my Circonus or whatever. But there are times where you're convinced that there's a specific problem with a specific component, and if that component kind of exposes all of this stuff in a way that makes the operator knowledgeable, then you win a lot. So like, don't underestimate like a decent UI, like going in and exposing the telemetry and being able to click on one and show a histogram. So like in a previous slide, this, like that's not Circonus doing that, that's the product, like that's built into the app. So when I'm running the database, I can do transactions against it, but I can also load the database in a web browser and see all the histograms. And that is like a whole 300 lines of JavaScript. That was all it took. It was really, really simple to expose that because I embedded metrics in the telemetry in the product. I used a library that was already there. I exposed it. I used D3 to draw it. Like all this stuff already existed. It was not a heavy lift. It took about, I don't know, probably about a week's worth of engineering work to generalize that entire framework, and then people all across the organization can adopt it into their own apps. So I don't need a third-party product or a third-party interface to be able to do that, which is really nice. So the second thing that we learned in all of this was that you end up having to codify the operational experience that you have running a product. So how many people run a SaaS or run some sort of service that delivers to somebody else as opposed to just building software that goes somewhere? I assume it's SREcon, so like site reliability implies you have a site. But one of the things that happens is that in order to run a site really, really well, a lot of the experience of the SRE organization is really that, it's experience. And it's not put in code as much as it's put into the organization's DNA. So you have teams, you have processes, you have the ways teams interact with each other. But the interesting part is that when you take some of those solutions and you ship them somewhere else, that experience doesn't ship with it. So it's really interesting. A lot of people say, oh, I wish we had access to Google's technology. I would say that if you just got Google's tech, you'd have a whole world of problems, right? In order to run the tech, there's just so much knowledge in that organization and infrastructure and things like that. But every organization is like that. Same is true for every organization I've ever worked with. So one of the things that I found incredibly useful is that in shipping the software, we had to, you can't just take all of your experience and put it in code because it's expensive and it takes time. So you end up looking at the things that you do to run your site reliably, and you start to codify them, right? You do an analysis, I do these 100 things, which one's the best thing? Which one's the most important thing? And you take that thing, and you take the experience, and you turn it into code that gets deployed. And now that entire team gets better. By taking their experience and writing it into code into the application or into the system that you deploy, you understand your processes better. And then you make onboarding new employees so much easier because they don't have to learn this organizational paradigm. They just have to interface with software. And when they have questions about it, they want to know how it works or why it works the way it does. They don't have to they don't have to occupy the time of another team member. They can go read code. Right? And that code has design documents. In this case, it definitely has design documents, but comes out of the runbooks and the organizational experience. So we found that by codifying all of these things, it tightened them up too. So a lot of the processes that we had, we thought they were really good, but it turns out they were kind of fast and loose. As soon as you try to teach a computer to do it, you realize kind of how sloppy you were as an organization doing it. So you get a lot of rigor around how you do these operational things. This is stuff like, you know, how do I detect when the system is going to run out of capacity? How do I do capacity planning around that? What happens when I run out of disk space? What are my remediation tasks for that? What happens when the system crashes? What are the order of operations to start everything back up in the system? Like, the last thing you want to do is to be on your 400th phone call with a customer repeating the same information to them, right? So what you do is you put all of that in code. You build the orchestration for that. You build all of that stuff into the code. So instead of downloading your old data and putting it in Excel and doing a linear regression, you just kind of build it into the code, and the database tells you, hey, given the last 2 weeks of usage, I'm going to run out of capacity in 78 days, right? Like, you put it in the code, and when you've done that, you realize that your original things that you were telling clients were slightly wrong the whole time. So you've told 400 people to do something sort of wrong. But once you've put it in code and you've tested it, you realize that you can make it a lot better. So, and the thing is that, and I think this is kind of generically true about anything. So every effort to bring SRE techniques into software engineering made those SRE techniques more accessible and useful to everyone, not only our clients, but our own internal staff as well. But I think that that's true about every sort of technique. Every valuable thing that you do in the organization, when you start to codify it, it really forces all of the people in the organization to start thinking about it. And that's actually the most powerful thing, right? You get a whole bunch of people trying to dissect it. It's like competing in code reviews. You get the one code review, which is like, yeah, it looks good. You get one person find a bug and another person find a bug. Now everybody thinks, okay, let's all do this. Everybody pours into it, and you get an incredibly kind of a profound result out of that. So I think that when you can align people to really think about how to apply certain techniques in different ways, you end up generating value all the time. So that is it for the talk. Does anybody have any questions? Mr. Looney. I can repeat you if you don't want to get up.
Is there ways to get eBPF data remotely without SSHing in?
So the question is there a way to get eBPF data remotely without futzing around, SSHing in? There aren't any remote daemons for that I'm aware of today. I will say that eBPF, like dtrace in abusive mode, is super dangerous. Not only can you see everything in the system, you can also change things in bad ways. So it's a little bit dangerous. So is SSH. But I'm not aware of any like kind of good fabrics to do that. So that Cloudflare has a solution that turns eBPF into Prometheus metrics. We have a solution that turns it into Circonus metrics. The downside of Prometheus metrics is the histograms are horrible, and horrible histograms in Prometheus. But I think that the real challenge of the eBPF is that for both of those solutions, that's when you already know the question you want to ask. Right, so it's really good for monitoring data and collecting performance data, but if you want to interrogate the system and ask the question you didn't know to ask, there aren't really good kind of map and reduce frameworks across large clusters of machines for either dtrace or eBPF for that. Not today. That's the future.
First of all, thanks for the talk. I really enjoyed that. I had a question about, so you mentioned a lot about kind of like building in the metrics and telemetry into the product itself, and like having like very fine resolution data, right? And that's, in theory, that sounds really good. But when you're running like hundreds of services on like thousands of hosts, there's a trade-off there. Like, the more data you need to store, there's more like, effort in building that into it, as well as like storing the data. So how do you make that trade-off?
I would say that there are two facets there. One is the effort of building it in. And I would say that with good coding practice, you should be able to reduce that error to that effort to epsilon. Right? It should be real. Once you've built the framework and how you want to track things like latencies, they should be part of how the service is built. A lot of those go into whatever framework you're using. You kind of retrofit your framework, and then everybody just wins. Mm-hmm. So I think instrumenting everything is critical. The other question is so now so we have customers that literally have 10 billion streams of data, right? Mm-hmm. So I think there's a fallacy that you have to store it all. Like, just because you're tracking it doesn't mean you need to store it. And it does feel a little guilty to like be instrumenting something and then like ignoring it. But I would say that the return on investment on storing metrics is still not perfect. I think if you have 100 million or 1 billion metrics, it's not a big deal. But if you have 1 trillion metrics, we're not at the place where like that makes financial sense for almost anyone. So you can always track them and store them later, right? What you want to do is when you do have a service issue and you show up, that you don't need to go instrument and redeploy. You can actually ask the question. And a lot of times in the service frameworks, and Circmetrics doesn't do this yet, but it's on the roadmap for it, is that a lot of them will keep their own internal time series for like 15 to 30 minutes to an hour, something like that, right? So even if you're not shipping it off the box and storing it forever, the app itself can give you like a little trend line of where it was. Which is usually enough context to decide whether or not I regret not storing this. I'm going to go add this and permanently store this.
So to follow up on that, like, I think one of the reasons why this is hard is it's because it's hard to compare the cost of like storing these extra metrics versus like the cost of like the operational workload that you have to go through. So I was just wondering, like, if you have any thoughts on like how do you put a cost against operations so you can make these trade-offs?
I will say that the cost of disk storage is forever falling, and the cost of operational talent is not. So I think the lines go like that. So that's clear. And I would say that metric storage has gotten really cheap. I mean, it's just. I mean, what used to take 1,000 machines running OpenTSDB, you can do on like 15 machines now. And if you do it in the cloud, like everything you store this year, every year that it goes by, it's actually cheaper to store it, right? Like, because you just actually, the cost degradation of the long-term store is there. So I would dare anyone, other than some of the major providers, to go instrument their apps and come up with more than like a billion streams of data out of their infrastructure, which I think is super affordable to store.
Thank you.